Good evening, friends. I think we can start. So, so week six covered about exoskeletons, robotic exoskeletons, and basically why do we need exoskeletons? What are their advantages? And it in lectures you have seen how to like control small exoskeletons. Basically, exoskeletons for hand and fingers. So that was the topic covered in the last week. So the assignment again assignment is not more towards the like numericals and problem solving side. It is more towards basically recollecting information that you have received in the lectures and whether you have understood them or not. So yeah, I will also try to again highlight some major concepts, and along with that uh, I will discuss a few questions. Yeah, so basically while discussing questions I will try to cover up some theoretical concepts which have been discussed in week 6. So yeah, the first question is pretty straightforward. Skeleton lying outside the body is exoskeleton, and the example is crab. So exoskeleton and endoskeleton are the two the two terminologies basically. Exo and endo as these prefixes, they mean outside and inside basically. So the crab has a shell, that is a exoskeleton, and like turtles or tortoises, they have the shell outside them, so that's the exoskeleton. Endoskeleton, like all vertebrates that we have inside our bodies, that's the endoskeleton. So why do we need like robotic exoskeletons? So the question is why robotic. I will write exoskeleton as EXS just to save some effort. So why robotic exoskeletons? So the idea behind them is to that they might enhance our capabilities in some way and also like protect us from certain things. So basically this could be the two obvious advantages. Obviously you can think up of more, but these two could be some obvious advantages. And like in fictional works, we all have seen such tools being used basically. So like a person sitting inside and or wearing an exoskeleton is lifting heavy things, moving heavy things around and throwing things. So basically it gives an impression that that exoskeleton basically helps or basically makes possible what a person cannot do on basically just using human strength. So the advantages we can write: advantages, or you can also say like objectives that we have while designing such exoskeletons. So first would be enhancement of strength. Then there would be like additional support or protection. Protection. And it can also like enhance or provide like some mobility. Enhance. This is applicable, let's say, let's say s- there's a person whose lower limb is not functional, or you know s- sort of like paralyzed and all. So a exoskeleton can help that person to walk by providing it support and improving the mobility of uh, the actual leg. Right. So also, yeah, these are basically the common advantages of having an exoskeleton. Which brings us to the next question, which is like similar to that only, that what are the benefits of robotic exoskeleton. And the first option is augments the human weights. Obviously it does augment the weight, like the weight overall increases, but it is not a benefit as such. Augments the size of human wear. Again, this is also not a benefit that we are looking for. What we are looking for is enhancement of strength and durability of human wearer. So that exoskeleton will, let's say a military purpose exoskeleton, so that can that can protect the soldier wearing it from harsh conditions, and all the things that happen on the battlefield. So, and also help him to carry heavy baggages, that would in turn help the soldier to complete longer missions, because they don't have to carry all that weight using human strength. They have that exoskeleton on themselves too. Obviously, carrying exoskeletons is itself a task. So again, therein lies the trade-off basically. So if we want robotic exoskeletons to be of actual help, then they should be like lightweight, right? So these are like very obvious points. So they should be lightweight, they should be comfortable to wear, because then only a person can wear it and work for long hours. And like the interface basically, so the user interface should be you can say smooth, and it should be durable. So again, these qualities we look for in a exoskeleton. In robotic exoskeleton, to be precise. Robotic exoskeleton, right? So again, this is a direct question from the lectures. All these 4 points have been discussed in the lectures, that the robotic exoskeleton provides support, protection, enhancement, sensing, and data fusion. So support we have seen, right? Protection also, and enhancement. First 3 points we have just discussed, right? Sensing and data fusion, what you can understand is that, when there is a robotics, like a mechanical or a man-made system, there would be, we can basically incorporate lot of sensors in on them, various kind of sensors. And there could be sort of a screen or something like that, where the computer of that exoskeleton basically is crunching all the numbers up and giving us some useful insights into our environment basically. So I personally like, you can think of it as an, so the Iron Man suit basically is a very advanced exoskeleton. So you can obviously think of that when you talk about exoskeletons. So sensing and data fusion is like collecting, because like manually we can just focus on certain things at a time, but exoskeleton with its own computing power and a range of various type of sensors, it can collect different kind of data. And data fusion means like collecting data from different sensors and you know basically merging them into some actionable insights basically. So collecting data from multiple sensors and processing them into actionable insights, right? So again, this is also a sort of enhancement, but not a physical enhancement in terms of uh, what how much information that we have. So basically enhancement of information availability, right? So the first, I guess the first lecture covered a general introduction to exoskeletons. And when we think of exoskeletons, like the examples shown there, they could be from like exoskeleton for a small part of the human body, like you just wear on your hands or fingers, or it could be a full body exoskeleton, right? So a three-fingered exoskeleton has been discussed, and again, it's a direct information-based question that what kind of actuation is this? So basically, first we have to understand what are these three referring to, right? So basically, these are like, you can think of it what we call as actuation and transmission, right? So actuation, what does it mean? Actuation means powering up something, moving something. It's not a static thing, the exoskeleton, right? It has to move. So there must be some actuation. Actuation means make something, in very like basic terms, it's make something move, right? So you can imagine that there is an exoskeleton and it has a full body exoskeleton, so it will have a lot of, you would think, motors and all, that are moving, heavy duty motors. Let's say it's a big exoskeleton that is enabling the person to lift heavy weights, right? So it would have very powerful motors in it that is providing that required force to lift those heavy objects. So here, but we are talking about a three-fingered exoskeleton, and you see two mechanisms that are quite popular in robotics, right? A cable-driven mechanism and a direct-driven mechanism. So let's like see what both of these are, right? And before that, so actuation are there is a a lot of variety in how what are the kinds of actuations that are used, not only in exoskeletons but like in general, uh, in various kind of robots. So let's just name a few of them. So like it could be direct driven. So direct driven, what does it mean? As the name suggests, it means that the motor is directly connected to the link it is actuating, right? So motor directly powers the link, right? So basically, if let's say there are like three links, right? So in a direct driven system, there would be a motor here, there would be a motor here, and there would be a motor here, right? So first motor would control the first link, the second motor would control the second link, and the third motor would control the third link, right? And direct driven also means that we are directly, like, there is no transmission like of like gear train and all between the motor and the link. So it's just like you are connecting the output shaft of the motor to the link, and straight, just the motor directly powers the link basically. So it's called the direct driven mechanism, right? in the in the cable driven mechanism, so we use cable and pulleys. We use cable and pulleys to transmit power, right? So in the direct driven case, the power source for each link is there at the base of that link itself, right? But in cable and pulleys, right, so the motor could be somewhere, and it could be powering multiple links via these cables and pulleys, right, to transmit power. So basically you can think of it as that the motor is here, right, and basically there is a cable, right, going over a pulley here, and here is the link, right? So something like this. So what are the, like, when do we prefer, especially talking about this three-fingered exoskeleton, what are the basically pros and cons of each of these? So cable and direct, right? Right. So first is that cable driven, we have less number of actuators. Less number of actuators. Why less number of actuators? Because you are not powering one link only from one actuator. One actuator transmits power to several of the links using the cables, right? So we have less number of actuators. Since there are less number of actuators, the control becomes simpler. So control is simpler, right? Then since less number of actuators there and control is simpler, it will be easy to build, basically. Easy to build because one reason is that you would, in the direct drive, as we will see. Okay, let me just first also compare each point for direct drive also. So obviously in direct drive there would be more number of actuators. Generally it would be equal to the number of links that we are actuating. So let's say there are three links, so there would be three actuators, one at each joint. So more number of actuators, and this in turn makes the control more complicated. Now here we are focusing, on a specific type of exoskeleton, that is this finger exoskeleton. So in finger exoskeleton, you would imagine that it has to, so the person has to wear it over one's finger, right, or one multiple fingers. So if we use direct drive mechanism, then at each joint you have to put an actuator, and since you have to make it lightweight and comfortable, and it has to power the link also, so you would need very small, but which has some good enough power also. So finding those kind of motors is not easy, right? So it it becomes so motor size becomes a restriction, and it becomes difficult to build. Motor size limitation, right? We cannot like put big motors at the joints of fingers, then the whole purpose of making that exoskeleton will be defeated. Difficult to build. And so again, since in the cable driven one, the one actuator could be placed at the end of the hand, and all the fingers would be controlled using cables, right? So the hand itself will be lighter. So the hand is lighter, and you would imagine it's opposite in the case of direct driven, because we have motors at each joint. So there are multiple motors whose weight adds up in the weight of the hand, so the hand becomes heavier. The hand becomes heavier due to multiple motors on the hand itself. Right. So in this case, in the case of these finger exoskeletons, we can clearly see that cable is preferable, right? Cable driven is preferable. So this is preferable than direct driven. But we have seen the some like direct driven has some major disadvantages, but you can think of advantage also, which might not like offset its remaining disadvantages, but it's still an advantage. And the advantage is that in direct driven there would be very less, we would say very less transmission losses, right? In the cable driven, the source is somewhere, and the cable is transmitting the power to the links away from it. So there would be some losses in the transmission. In the direct driven, you are directly connecting the output shaft of the motor to the link. So basically it would be more efficient way to power the link. But yeah, and direct driven are like still used in many different robotic applications. So in this specific application, we are preferring cable driven mechanism, right? And this exoskeleton, that finger exoskeleton, as we discussed for the full body exoskeleton, this should be like lightweight, comfortable, uh, reliable, and durable, right? Apart from this, just as a general comment, like there are different types of uh, basically actuations that is used in robotics applications. So apart from direct driven, cable driven, you could think as like uh, similar to cable driven, there could be belt driven, or like chain driven. Belt driven, like it's not a smooth belt, it's a belt which has teeth basically, and it goes over gears and it is used in transmitting power. And there are like series elastic actuators, something called as series elastic actuators, also known as SEA. And finally, there are like pneumatic actuation devices. So pneumatic means using compressed air to control the or actuate the links. So pneumatic exoskeletons, like small hands with fingers that are powered using pneumatic actuation, you can also find out. Basically, you can see those, like there are quite a few videos of these in public domain, so you can just watch it. Okay, so in the lecture, it was described that the exoskeleton was then used for a grasping task. Grasping means holding an object and applying a certain force onto it, right? So, like this whole, give me just a minute. Right, so if we are creating a exoskeleton, so the most common task that it would do is to hold things, right? And to hold things, what we would need that it applies the force that is required to hold that object, otherwise it would not be able to hold. So, and it should not happen that, let's say we are holding a, let's say you are holding a fragile object, let's say you are holding uh, a glass, right? So if you apply a lot of force while holding that, it would break, right? And if you are holding a heavy object and if you are not able to apply the required amount of force, then it would fall out of the hand of the exoskeleton. So basically this points to the fact that we need what we call as force control, right? So force control, a very important thing in designing these exoskeletons, right? So basically what we would say that, okay, we have a desired force, right? What we have is a desired force, that okay, I want to, let's say for simplicity, let's say we are just now thinking of just grasping an object and just holding it, not letting it fall. So we would need to apply a certain amount of force and continue applying that magnitude of force for that duration for which we want to hold the object, right? So that would be our desired force. It could be, and again, that's what the question is here. The desired force input, it could be anything, basically a single step input, right? That single step input would be right, like no force and then a certain force and then keep applying that force, right? Multi-step input, that okay, maybe there would be some force, then there would be some force, then maybe leave it or decrease the force, and then again. So this could be irregular, some random trajectory would be there, apply this kind of force. It could be like multiple type of thing. Basically the shape of the desired input force would vary from task to task basically. So all of the above is the right answer here. Now coming back to our discussion, so we have the desired force, right? And what do we need? We need that the actual force, right? So F actual, they closely follow each other, right? We want this to be close to the desired force, right? And for this you would imagine that, okay, you have seen in the position control, velocity control, right? So similarly we have now here force control. So there you would apply some feedback, right, based on gains multiplied with the error, right? So whenever we want to control something using feedback, what we do, we find the error between the desired and the actual, then we multiply it with a certain gain parameter, and then we use it to decide the correction basically, like whether you need to increase or the force or decrease the force. So in the lectures there is a very nice block diagram of that force control. I would redraw that, so just uh, give me a couple of minutes. I would explain this. So let me first draw this completely. We are almost done now. Just join this up here. This is F actual, and here we are putting F desired. Right, I guess we are done with this diagram. So first of all, let's write the control expression basically from this block diagram, right? So let's start from here, from this point. So from here, the theta value, right? The theta value is the, basically you can imagine joint angles, right? So joint angle commands goes to the exoskeleton, that, okay, move the links. Let's say there's a finger with 3 links, right? So we would give a command that move the angle to this angle, move the links to this angle. The exoskeleton will execute it, right? You would imagine that let's say you are holding an object, and you want to increase the force on it, right? So you would like bend your fingers more towards towards that object, trying to press that object more, right? So like I'm trying to say this to give you an intuition that okay, how changing the angles of the links basically changes the amount of force it is producing, right? Maybe you can also relate it to the in some way to the force ellipsoids that we had seen last week, right? That in different configurations the end effector will produce different force, right? So to increase the force or to decrease the force, you would change the joint angles of the links basically. So let's start from here. We give certain command, right? So we give the we give the joint angles command, right? That goes to the exoskeleton. The exoskeleton executes that, and upon executing it there would be a change in the force. It would increase or decrease, whatever, right? So that change is measured by the force sensor, and the force sensor is on the object that we are holding, right? On the object, right? And that value, that measured value, is the f actual life, right? And here you are seeing that it is being subtracted from f desired, right? This is the desired input. So this is the desired input, right? So what will come here? It will be f desired minus f actual, right? Then this term, this is the gain basically, similar to the gain that you had seen in PD control. Whenever we were multiplying the error with certain constant, that's a gain value. So this you would have to tune that okay, what will that gain value do? It's a reflection of, or it's a measure of something. You can imagine that if the how the basically the controller reacts to differences in desired force and the actual force input. Let's say the gain is very high, then what it will do, it even if there is a very small error, it would try to correct that, right? So basically you have to tune the gain according to your application, and then this k times f, the difference in the forces, we are multiplying it with the transpose of the Jacobian. So this is the end effector Jacobian, end effector Jacobian. And what does this give? This gives the joint velocities, the new joint velocities, and we integrate the joint velocities to get the new joint angles, right? So this is the loop, and once again the new joint angles will be sent to the exoskeleton. Again there would be some new force measured that would go back again here, right? And this loop will go on. So this is the control loop. So this is the force control loop. Force control loop, right? All clear till here? So we can write the control law here very simply. Control law is the mathematical expression of what's being described by that block diagram, right? So basically what we are doing, we are computing theta dot as J transpose k times f desired minus f actual, right? So this is the error term, delta f. So this is a control law. right? And theta is integral theta dot dt. So in actual practice, you would use numerical schemes to integrate basically. So, and also in the lectures it has been shown that this control law is basically asymptotically stable, right? By using the Lyapunov stability criteria, it has been shown. So on a long enough time horizon, the error would not blow up. It is guaranteed that the error would not blow up, and that's what we want, right? That the error should go to zero as time tends to infinity. So what we need, that as t tends to infinity, delta f should tend to zero, right? And we call this as
Didn't catch that. Could you try again?
asymptotic stability, right? So this is asymptotically stable, this control law, right? Okay, so again, we are staying on this relatively the same topic. The relationship between the joint torque and the end effector force is given by. So this is a very useful relationship that you would use quite frequently in any robotics applications, and in theory and practice everywhere you would use this relation. So let's try to see where this comes from, right? First of all, let's see how the Jacobian is defined, right? So Jacobian, let me what is this? This is end effector Jacobian. And let me also draw a sample system just for reference. So let's say there is a fixed base manipulator, right? So this has 3 degrees of freedom: first, second, third, right? So the joint angle vector is given by q. Let's write that as q1, q2, q3, right? And the position of the end effector, let's say it's given by x, right? What is x? X is the position of the end effector. So if any of the quantities are expressed as a function of joint angles, then we call it as joints, that the quantity is expressed in joint space, right? And if the quantities are expressed in terms of Cartesian coordinates, or basically xyz, so that we call as, you would call it as end effector space. And there are other names also, operational space and all. So end effector space or operational space. So, and you would see that quite commonly we keep switching between these two spaces, joint space and operational space. We do computations in whichever space it is necessary, required, or in whichever space it is easier to do. So we keep switching between joint space and the end effector space.
Okay, I found this on the web for require.
Sorry for that. Yeah. So now, how is this J being defined mathematically, right? So J is differentiating the end effector position with respect to the joint angles, right? This is J. Now we can write this as del x by del t into del t by del q, right, where t is the time. So basically time derivative of the end effector position into 1 by time derivative of the joint angles. So this implies that if we take this second term on the side of j, so it would be j times del q by del t is equal to del x by del t. So here comes a very useful relationship that you would see, is that velocity of the end effector is Jacobian of that end effector multiplied by the joint velocities. So basically what this does, this relationship, it, how are the end effector velocities related to the joint velocities, right? Now this is the relationship. Now using this relationship we would arrive on the this tau is equal to j transpose f relationship, right? So let me define the power, basically the power delivered to the end effector. Right. So again here what we would use, two terms. We would use F, right? So F is the end effector forces in end effector space. End effector forces basically. So this is in E space. So basically you would say that this is in Cartesian space. There would be fx, fy, fz like that, right? And this torque, what you would say, generally we say it as a torque, but more formally it can be said that these are generalized forces, or you can say that they are forces in the joint space. You can also call it as joint space forces. Rather than calling it simply torque, you can call it as this joint space forces, right? Because you would imagine that torques are being applied to the joints. So we would write the power delivered to the end effector in terms of both these quantities separately. So power is power is force into velocity, right? So it would be the end effector force dot with end effector velocity. Cool. And we would write this in term of the joint space forces also. So that would be tau dot, and what is power? Tau omega, right? So omega means joint velocities. So that would be q dot, right? Now both are power only, a power delivered to the end effector. So we can equate both these expressions. So 1 and 2, right? So 1 is equal to 2, right? So what we have is F transpose X dot is equal to tau transpose q dot, right? Now here we will use this relation that x dot is jq dot, right? So on the LHS we use that expression that x dot is j times q dot. Now q dot gets cancelled, right? So what remains is f transpose j is equal to tau transpose, right? Now if we take transpose both sides, what will we getting? Tau is equal to j transpose f, right? So this is how we arrive at that expression. So basically what the conclusion is that the joint space forces, that is this, the joint space forces are related to the end effector space forces through the end effector Jacobian, right? Now in the force control experimental setup of the finger exoskeleton, where is the force sensor placed? So this is straight away from the lectures slides, and if you would see carefully, you would see that the force sensor has been placed on the object and not on the finger, basically, right? And yeah, so I guess nothing much to discuss on this question. Yeah, moving on to the next one. So this example is from the concept where it was introduced that we can use basically neural networks to control these exoskeletons, right? So now you can, now on a very general level, right? So control in robotics, you can say, is of two types. One is model based, and other paradigm is using learning algorithms, which includes all these reinforcement learning, neural networks and all, learning based. So in model based, what do we have? We formulate the model mathematically. We try to formulate the model mathematically and as accurately as possible, or as per our requirement, and then we basically use some classical control algorithms to let's say feedback control and all, to find out the control commands. So in model based, what are the advantages? Like, since so advantages and disadvantages are that you would need to formulate the model mathematically, and how good is your model based controller sometimes depends on how well you are modeling it. So how good is your model? And it also involves like some matrix computations, taking inverse of large matrices and all. So people are like now trying out quite frequently learning based control algorithms also, where you would see that there is no need to explicitly model the system. Basically, let's say in the case of neural networks, so you would just relate the input and the output using a neural network, and while training it would tune its weights to achieve our desired objective, right? Let's say it's tracking a trajectory, as you have seen in previous lectures, right? So here also in the lecture it has been shown that KSOM based kinematic control of exoskeleton. So what is KSOM? So what is KSOM? So this is abbreviation of Kohonen self-organizing feature maps. Kohonen self-organizing feature maps, and this is an example of unsupervised neural network learning, which is the question also in here. Unsupervised neural network. So why do we use why can't we use supervised neural networks? So why unsupervised NL? Because for supervised learning, what do you need? You need that if this is the input, then this is the output. You need those kind of training data sets, basically labeled data you would need. In this case, what you would need, then you would need that, okay, if the finger is in this position, then the joint angles are this, right? And for this itself, you would need forward kinematics and inverse kinematics, and that's the thing itself that we are trying to avoid, right? So supervised learning is not possible here, right? So because the data that represents the joint angles corresponding to the desired position is not available, basically, right? So to avoid estimating the kinematics and computation of pseudo inverse, what do? We use unsupervised neural networks, right? And in that we use KSOM, right? So why unsupervised? Because the joint angles corresponding to the desired position is not available. Why are saying it's not available? Because we don't have the model. We are assuming that we don't have the model, or we are not wishing to compute the model here. Because if we compute the model, then it's same as model-based control, right? So we are trying to control the exoskeleton without explicitly computing the model, right? So, and interestingly, however, it has been shown that KSOM is able to KSOM is able to control KSOM is able to control, but its performance is not as good as the using what we get using inverse kinematic, but its performance not as good as inverse kinematics, because inverse kinematics in this case you can solve exactly that. Okay, if this is the end effector position, then you can get a closed form solution of what the joint angles would be. So obviously it would be much more accurate. It might be more computationally tedious, but it's more accurate, at least in this case, than KSOM. But yeah, KSOM also does the work. Now the next is what are Hjorth parameters? I guess I'm not sure about the correct pronunciation of this. So basically Hjorth parameters are used in signal processing, basically getting features from signal processing in time domain. And these three are the all three are the three Yorth parameters: activity, mobility, complexity, right? So let's say, so these are related to signal processing, and specifically like EMG, EEG, signal processing from those kind of devices. So let's say we have a signal YT. YT is the signal. Then we can define these three parameters. First is activity, right? So activity is defined as variance of this signal. Variance is like how much the signal is. So variance, does it signify? Like how is the data spread around its mean? That is variance, right? So that is activity. Second is mobility, right? So mobility is defined as square root of variance of the first differentiation of that signal divided by variance of the signal, right? This is mobility. And the third one is complexity. So complexity is defined as complexity is defined in terms of mobility. So mobility of the first differential of YT and mobility of YT, right? So these are the three Yorth parameters, and they are used in signal processing. And finally, we have again a straight question from the lectures, that what are the biosignals used in study for the control of robotic exoskeleton. So in the last few slides, you might have seen that we are trying to control the exoskeleton by from the signals from our muscles basically. So it's like basically you move your hand in a certain way, move your fingers in a certain way, and the exoskeleton will also move in that same way, trying basically replicating that. So for that purpose, we use EEG and EMG. So EMG basically is used to read signals from muscle fibers. Uh, the full form is electromyogram, I guess. And yeah, so EEG and EMG. EMG, we also use surface EMG, not invasive EMG, because invasive EMG is painful, and surface EMG without pain it does the job. So yeah, I think this is pretty straightforward. So I think while doing this assignment, we have covered not in detail but major concepts from each of the lecture slides. So again, I think from my side this was the content for discussion. If from your side, if you have some specific queries, then in the assignment or uh, in general in this week's content, then you can ask. Okay, guys, so I think the assignment that you have to do this week is pretty much similar to what I have discussed. Some questions might be exactly the same, I'm not sure. And as I said, most of the questions are based on information that is being directly provided in the lecture slides, so you can just refer to them in case of any doubts. Okay, so I think this is it in the today's discussion hour, and we will meet next week again. Thank you guys for joining.
Thank you, sir.